Farina on joint work with me on symbolic execution using symbolic execution for verifying differential.
Hello everybody, I'm Gian Pietro, and today I will be talking about relational symbolic execution for differential privacy. Some of you in the audience might have already heard a few things about this topic, but I apologize if it's going to be a bit boring. Anyway, so I'm a programming language person, and in particular I come from the formal verification community. And during this week, there were already 2 talks about formal verification, and in particular, the main idea of their work was that they would build an engine based on some kind of type system or logics whose main goal was basically to take an input, a piece of code, and a specification, for instance, the specification of differential privacy, and then output yes, if the program was indeed differentially private, plus some evidence of this fact that we call proof or formal proof. And in the case where the program wasn't differentially private, then the program would not say yes or would say I don't know. And I'm looking at this kind of problem from a different perspective, in the sense that I'm looking at what happens when the proof fails. And in particular, I'm thinking about an engine that, describing you an engine that takes an input, a source code, and a specification, differential privacy, and it outputs basically no when the program is not differentially private, plus some evidence of this fact, some information. And this information, this kind of feedback could help the developer to fix his code or to understand why the formal proof fails if the developer has some background about formal methods. What counts as kind of feedback is a counterexample, for instance. A counterexample to epsilon differential privacy for a program C would ideally look like as a pair of databases, D1 and D2, that are adjacent, and an event, E, a description and an event, such that the output distribution on the 2 runs of the program, when we feed it with these 2 databases, assign mass to this event that basically violate the privacy bound that we want to respect. And there have been already works on how to kind of automatize this kind of search, but some of them were kind of based on a statistical approach, like approximating the output distribution of the program on 2 runs and trying to see approximately where the bound was violated. What I'm trying to look at is to use a different approach, which is called symbolic execution, which is a standard technique in program analysis. It has been studied since from the 70s. But exactly, I want to use this approach to look for bugs and counterexample for differential privacy. Now, since I'm aware some people here might not be familiar with the concept of symbolic execution, I try to give a crash course on symbolic execution in a few slides. And the idea is that we can take this piece of code as a very simple example. And this piece of code just takes an input some integer x, and it branches on the predicate even x. And if even x is true, then it assigns to the variable in output x squared. Otherwise, it outputs x squared minus 1, okay? And this is the piece of code. While the specification, there are many ways to describe what a specification is, and one way to do that is to provide two predicates. One is what we call usually precondition, and it's some kind of predicate on the data of the program, and it's some assumption that we can assume while we analyze the program. And then the other part of the specification, it's called postcondition, and in this case says out greater than 0. And it's something that we want to have no matter what, whenever we executed the program starting from a state where the variable x is greater than 0, or better said, when the precondition is true. And let's see how we can, so this precondition, this triple is not valid, obviously, in the sense that there are values of x which satisfy the precondition, but that lead to a final state where the postcondition is not true. But the question is how we can do this, how we can understand this using symbolic execution. And the idea is that exactly how the name says, we execute symbolically the code, and now executing symbolically the code means that now the variable x doesn't have a concrete value, but it has a symbolic value. And this means that it denotes a set of possible concrete values. And this set of concrete integers gets refined during the symbolic execution through the creation of new constraints that refine the variable x. But now the first execution of our simple program is a branch instruction. But we don't have a concrete value for x, so we have to really follow both branches. And in one case, we follow the true branch, and we assume in that true branch that x is indeed even. And then we create a new symbolic relation between out and x, which says that out is equal to x squared. But we don't have concrete values for them. They're just symbols. And in the other branch, we do the same. And we create, though, a different relation between the symbols x and out. Now, the idea is that we can, in this way, create what we call in the field of path conditions, PC1 and PC2, that denote a set of possible tracks. A set of possible traces of the program. And the idea is that the path condition is true if all the path condition imply logically the path condition. And this is obviously not the case because the path condition PC2 does not imply the path condition. And this check can be done by a standard off-the-shelf SMT solver or constraint solver, and that when finds out that the implication is not valid, gives us back a counterexample, in particular a set of values that satisfy the path condition, the path condition, PC2, but that lead to a state where the path condition is not true. Okay, this is a very short crash course on what symbolic execution is, and the idea is that we want to apply this concept to differential privacy. But differential privacy, as we all know, is a relational property in the sense that we are always talking about two runs of the same program on two inputs that are related, and we want to prove some path condition which talks again about outputs that are related. So the idea, I'm gonna now abstract away from details, is that we are gonna consider two symbolic executions paired up. And these gray triangles mean basically that the program could have loops, so it could be infinite in theory, but we always pick a number of maximum iterations to stop the execution. And the idea now is that we don't follow only one track, but we basically start from relating states and then we follow paths that are related. Okay, and during this relational symbolic execution, we don't only gather constraint relative to one path, for instance, the one on the left, but the constraints are going to be relational as well. So they're going to relate related states. And so this is what we would like basically to use relational symbolic execution for. Find counterexample to this kind of generalized relational triple, where we are saying basically that if we have our precondition that says that our two databases are adjacent, and we execute the same program on these two databases, we end up in a state where basically the definition of differential privacy holds. Now, dealing with this kind of with this kind of probabilistic properties symbolically, it's very challenging for SMT solvers nowadays. So one idea is to approach this problem is to get rid of probabilities and instead going back to standard first order logic. And we can do that by basically taking the only instruction that generates in our language, in our abstract language, generates randomness, and adding this new kind of axiom to our system that says that every time we are sampling in the two runs from Laplace that might very well have different means in the two runs, we can create a new relation between the samples. That's the one that we find in the postcondition. By paying some of the budget that we want to spend, where the budget is our epsilon variable. So, and this is exactly what this axiom says. If we assume that our database are adjacent, and then we have some bound between the differences of the means of the Laplace in the two rounds, and we have until now spent V of our maximum amount of budget, then we can do the sample and assume that the samples are related by that relation in the postcondition, but we have to pay for that. But now notice that this K and K prime are symbolic again. And the idea of finding counterexample or finding proofs is going to boil down to ask whether such K exists or not. And in case of multiple Laplace assignment, if there is at least, if there are enough, if there are X number of Ks that allow this, this kind of axiom to be applied enough times. So this turns, boils down, I mean, this brings us to a new way to prove or disprove differential privacy, which is the following and doesn't have any probabilities involved. In particular, now what we want to prove is that starting from two databases that are adjacent, we execute our program, and we always end up in a state that satisfies this postcondition, which basically says that every time the output variable of the program C on the first run is equal to some arbitrary value I, then also in the second run, the output variable is equal to I, but the variable epsilon C that denotes how much of my budget I spent so far is less than or equal than epsilon. Now, we can see this in an example. An example could be sparse vector, which is a standard algorithm that basically takes in input a bunch of queries. We assume they're counting queries. Takes in input a database and a maximum number of iterations, let's say, of positive iterations. And the idea of sparse vector, for those that are not familiar with it, is that we want to answer top or bottom, and we answer top when the ith query on the database is greater than the threshold, and we output bottom when that's not the case. And we want to do this privately, and so that's why we add first noise to the threshold for some reason, but we importantly add noise to the query at every iteration. Okay? And this has been proved private, epsilon differentially private, and it's been proven both with pen and paper, but also formally. But the idea is that someone implementing this algorithm might think that releasing the noisy query could still be private. Or maybe it doesn't think of it, but just introduces a bug. And we could use relational symbolic execution to check that that's a problem. Because, for instance, in this case, we could explore the path in red. And this would be the constraints that I would gather from that execution. And then from the other execution and from the relational part of the execution, we would get the constraints in the second column and in the third column. I don't want you to digest all of this, but basically what's important is that the constraint in the first two columns, basically, that are the constraints gathered from the first trace and from the relational random assignments, basically, do not imply the same trace on the right. And in particular, this can be answered by an SMT solver, which would provide a model, a counterexample, for this implication. Now, this doesn't mean that the counterexample provided would be indeed a pair of databases that violate the privacy condition, because sometimes symbolic execution, in this case, provides also false positives. But this is still an hint to the fact that the formal proof didn't go through, and so the user might go and check his code for more information about it. Another example is the following. This is still another buggy version of sparse vector where we forget to noise the query. Okay? We noise the threshold, but we forget to noise the query. And now we can do the same. We execute in parallel, let's say, these two symbolic execution. And now I pick my favorite trace, which is that one. And this corresponds basically to the output top bottom. Because in the first case, we are below the threshold. And in the other case, we are above the threshold. And this generates this set of constraints, right? Where the queries are not noised and the output is bottom and top. And this is just from the left execution. Now we also have the constraints that are obtained by the relational, by the proper relational execution. And again, we notice that these set of constraints do not imply the right execution, the mirrored right execution. In particular, an SMT solver will be able to give us a set of values for these symbols here, basically. Q1D1, Q2D1, Q1D2, and Q2D2, which are namely the answers to the queries both on the left and on the right run. But in this case, we indeed get a counterexample in the sense that once we compute the probabilities of getting the event bottom top on both runs when the outputs, when the inputs are such that the equations on the first row here are satisfied, indeed we get a privacy loss which is infinite. This because if these are the values of the input, basically there is some constant probability of getting that event out on the left run, but there is zero probability of achieving that event on the right one. So this is a case where actually the SMT solvers was able to give us a counterexample. And I think I'm done, yes? And if there are questions, I'll take them.
So a distinguishing feature of what you're doing compared to some of the talks we heard earlier in the week about verification is the generation of counterexamples.
Yes. Yeah.
But then the question really is, how useful are those counterexamples to debug the program if the program is indeed buggy?
Yeah, I mean, for personal opinion, I mean, more than debugging the code, maybe it can help you understand why the proof of privacy fails, and because it gives really, you know, two databases that make the, you know, the privacy loss go above e⁻⁴. So of course that's a matter of personally, I would find it very useful to have some, you know, two databases that show why the privacy loss failed.
That's kind of like a very concrete certificate that
Yes.
it shows you why it's wrong.
Yeah.
It doesn't really help you find where in the code you need to. I mean, you made a modification in the code. Is there in some sense in which you get directed towards that?
I mean, that could be maybe. We could use like proof assistance, like type, approaches based on type system to see where actually the proof fails. Once we you know, execute the programs with those specific input, we could see where the proof fails, and that might give us an idea of why the proof fails. That's one way I could look at it.
Does this symbolic execution allow quantifying over unbounded size inputs? And then I guess there's also the question with like something like sparse vector, number of iterations.
So in theory, if you make, I think the question maybe is that you could make symbolic the n, right? The problem with that is that then when you execute the code, basically you never know when to terminate because you never know when you reach the end. So the standard approach is to just put a fixed constant bound and see if within those iterations you get a counterexample. Yeah.
Yeah, but in our method we do more than that.
Yeah. Okay. Yes, there is a way to get around that. Would be to provide the loop with invariance. Like you say, you provide a predicate that you know it's true after the loop, and then that allows you to skip the whole loop. But you might lose some information, and then a counterexample that you get might not again be a real counterexample. Yeah.
Okay, let's thank Gian Pietro.